طبعاً عزیز ئەم کاتتان باش بابەتی ئەمڕۆمان تەواوکەری بابەتی پێشووە واتە لە بابەتی Introduction to Solid State Physics لەژێر ناوی نیشانی Chapter 2 Crystal Structure Part B بەشی دووەم لە Crystal Structure لە Chapter 2 Diamond lattice structure exhibited by carbon silicon Si and germanium Ge consisted of two interpreting face-centered cubic lattices displaced along the body diagonal of the cubic cell by 1 divided by 4 the length of the diagonal, also regarded as an FCC lattice with 2 atoms per lattice side, one centered on the lattice side and the other at a distance of A divided by 4 along all axes. That is to say, an FCC lattice with the 2-point basis. Diamond lattice structure is clearly seen in this figure. This is a diamond lattice structure. It can be seen how the atoms been arranged. I divide by 4 x bar plus y bar plus z bar, where A is a lattice constant. Diamond lattice structure also shown in this figure for the clearness of the subject. Here, it can be seen that 8 atoms in each corner, 6 atoms on each face. Here, 4 atoms entirely inside the cell. So 8 atoms at each corner, 6 atoms on each face, 4 atoms entirely inside the cell. Zinc blend, similar to the diamond cubic structure, except that the 2 atoms at each lattice side are different, exhibited by many semiconductors, including ZNS, GAS, ZNTE, and CDTE. GAN and SiC can also crystallize in this structure. Zinc blend. In this figure can be seen that two elements, Z and S, each Zn bonded to 4 sulfur tetrahedral equivalent, if Zn and S are reversed. Zinc sulfate crystallizes in 2 different forms, hexagonal and zinc blend, shown in these 2 figures. Here in this figure, red Ga atoms, gallium atoms, and blue As atoms. Equal number of Ga and S ions distributed on a diamond lattice. Each atom has 4 of the opposite kind as nearest neighbors. Can be seen that 2 types, red and blue atom. Hexagonal structure. This is the hexagonal along of the zinc blend lattice. Can be considered as 2 interpreting close-packed lattices with half of the tetrahedral sides occupied by another kind of atoms. 4 equivalent nearest neighbors, similar to a zinc blend structure. Certain compound semiconductors, ZNS, CDS, SiC can crystallize in both zinc blend cubic and hexagonal structure. This is a hexagonal structure. We have shown it before in the previous lecture. Gallium nitride, GaN, can be seen nitrogen phase and gallium phase here. Nitrogen and gallium constituents of the gallium of this zinc blend structure. Miller indices of lattice planes. The indices of a crystal plane, HKL, are defined to be a set of integers inversely proportional to the intercepts of the crystal plane along the crystal structure. HKL equal to H equal to 1 over x1, K equal to 1 over x2, and L equal to 1 over x3. Miller index for cubic structure. Miller index is used to describe directions and planes in a crystal. Directions are written as UVW, where UVW, integers UVW, represent coordinates of the vector in real space. A family of directions which are equivalent due to symmetry operations is written as UVW. Planes written as HKL. Integers HK and L represent the intercept of the plane with X, Y, and Z axis respectively. Equivalent planes represented by HKL inside the bracket. Miller index directions. Here in this spherical coordinate X, Y, and Z, a crystal lattice structure is seen. Here is, and the informations are given for X, Y, Z together with the Miller index is 0, 1, 1. Here, 0, X 0, and Y equal to 1, and Z equal to 1. So it is 0, 1, 1 inside the bracket, square bracket. Negative directions, here is given in negative directions, minus Y directions. So X will be 0, Y minus 1, and Z 2. So it is 0, 1 bar, 2. Bar means negative direction. Miller indices, equivalent directions. For example, equivalent directions due to crystal symmetry. In one is 1, 0, 0. That's the intersections with x-axis and do not intersect with y and z-axis. In 2, which is on y-axis, 0, 1, 0. So does not intersect with x-axis and z-axis, only intersects with y-axis. Number 3, 0, 0, 1. It means it does not intersect with x and y, while it only intersects with z-axis. Notations, 1, 0, 0 used to denote all directions equivalent to 1, 0, 0 inside a square bracket. These are the directions, x, y, and z. So it is x 0, 1, 0, y 1, 0, 0, x, sorry, y 1, 0, 1, x 1, 0, 0, and z 0, 0, 1. Here, it is a negative direction in y-axis, 1 bar, 1 bar, 1, 0, and so on with the rest of the figures. Example, the intercepts of a crystal plane with the x-axis defined by a set of unit vectors are 2a minus 3b and 4c. Find the corresponding Miller index of this and all other crystal planes parallel to this plane. The Miller index are obtained in the following 3 steps. First, identify the intersection with the x-axis, namely 2, minus 3, and 4. Number 2, calculate the inverse of each of these intercepts, resulting in 1 by 2, minus 1 by 3, and 1 by 4. 3, find the smallest integer proportional to the inverse of the intercept, multiplying each fraction with the product of each of the intercepts. So 24 is 2 by 3 by 4. This results in integer, but not always in the smallest integer. These are obtained in this case by multiplying each fraction by 12, resulting Miller index 6, 4 bar, 3. So 4 bar means in the negative direction of y. Negative index indicated by a bar on a top. Miller index of planes. Here in this figure and this plane, it can be seen x equal to a, while z and y equal to infinity. So the x-intercept is 1, y-intercept is 0, and z-intercept is 0 because it became 1 divided by infinity becomes 0. So the Miller index will be 1, 0, 0. Miller index of planes, again, here we have another example. X equal to 1, y equal to 1, z equal to 1. So the Miller indices are 1, 1, 1. Planes with negative indices, here, x1, y minus 1, z minus 1. So it is 1 bar should be. Equivalent planes, in this figure, it can be seen that a unit cell, here, a crystal structure on X, Y, and Z. Here, plane 1, 0, 0, and plane 1, 0, 1, and plane 0, 0, 1. So planes 1, 0, 0, 1, 0, 1, 0, 0, 0, 1, 1 bar, 0, 0, 1, 0, 1, 0 bar, 0, 0, 1 bar are equivalent planes denoted by inside the big bracket 1, 0, 0. Atomic density and arrangements as well as electrical, optical, physical properties are also equivalent. These are another examples of planes of intersections with the axis and the Miller indices under each figure is shown. The 110 surface is A infinity. Fractional intercepts 110. The reciprocal of it equal to 110. So the 100, 110, and 111 surface considered above are called low index surface of a cubic crystal system. The low refers to the Miller indices being small numbers, 0 or 1 in this case, as shown in the figure. Crystallographic planes, Miller index HKL reciprocals. It can be clearly seen in this Miller index in this crystallographic planes in this 4-plane and show. The 111 surface is A, so it is 111. Reciprocal also becomes 111. While for figure 2 here, we have intercept half A and infinity. So the fractional intercept is half 1 infinity. The reciprocal of it, reciprocal become 210. Symmetry equivalent surfaces. The 3 highlighted surfaces are related by the symmetry element of the cubic crystal. They are entirely equivalent. In fact, there are a total of 6 faces related by the symmetry elements and equivalent to the 100 surface. Any surface belonging to this set of symmetry-related surface may be denoted by the more general notation 100, where the Miller indices of one of the surfaces is instead enclosed in curly brackets, as shown in the figure. Angle between crystal directions, angle theta between directions H1, K1, L1, and H2, K2, L2 over cubic crystal is cosine theta. This is a very important equation. It gives you, determines the angle between the directions, and is can be remembered easily. Cosine theta equal to H1, H2 plus K1, K2 plus L1, L2 divided by the square root of the squares of H1 square plus K1 square plus L1 square multiplied by H2 square plus K2 square plus L2 square. So this equation can be used, and it is straightforward to calculate the angle between the directions of the 2 planes, H1, K1, L1, and H2, K2, L2. Miller index for hexagonal crystal structure. 4 principal axes are used, leading to 4 Miller indexes. Direction HKL plane, HKIL, example 0, 0, 0, 1 surface. It can be seen here. First 3 axes divided by indices are related. H plus K plus I equal to 0, or I equal to minus H minus K. Indices HK and L are identical to the Miller index. Rhombohedral crystal system can also be identified with 4 indices, and this can be seen clearly on this hexagonal crystal system. Thank you very much for listening, and wish you all success. Regards.